Okay, so pleased to our next speaker, Tudor Dimofte from Edinburgh, is going to tell us about categorifying the Schur index.
Thanks. It's really a pleasure to be participating in my first seminar of this series. It's really nice to be part of this community. Also, this is the first talk I'm giving on this particular project. So it's something that my student Wenjun Niu and I have been working on. Wenjun is at Davis. And he's, at least he started off as a student in pure math. And this project is really about sort of trying to tie together various constructions that have been appearing in mathematics with like the physics of what one would expect for things like local operators in 4D n equals 2 theories. And it's somehow like extremely closely related to Maddalena's talk, but coming at it from a slightly orthogonal direction. So 4D n equals 2 supersymmetric theories, not necessarily superconformal, have several different protected indices that count local operators that are BPS in various different ways. One of these, which is what I'll focus on, is the Schur index, the so-called Schur index, because initially it was related to Schur functions. So one reason the Schur index is nice is because the operators it counts can be described very simply as being in the cohomology of a single supercharge within the 4D n equals 2 SUSY algebra. And this supercharge is particularly nice in that it's what some folks call holomorphic topological. So what I mean by that is that like up to a rotation of spacetime and rotations of R symmetries and the choice of the charge, you can choose a splitting of R4. So locally, I'll just be working on flat space, and R4 gets split into a two-dimensional real plane and a one-dimensional complex space. And the significance of the splitting is that the image of Q in the SUSY algebra contains translations in the two real directions that I've called x and t, and anti-holomorphic translations in the z direction. And in particular, the sorts of correlation functions that Maddalena wrote down, though in this case, it's just correlation functions of operators in a supersymmetric theory. Correlation functions of closed operators will only depend holomorphically on the z coordinate. Or since we're avoiding collisions of supports, they'll depend meromorphically on their z insertion points. And that gives local operators in this cohomology a structure, the structure of a vertex algebra. And the way I've set it up here, it's a commutative vertex algebras. OPEs are non-singular. And that's just because, again, the way I've set it up, these operators can be moved apart in the topological directions in T and X. And so like collisions in the Z plane don't need to be singular. So this perspective was in particular studied by O and Yagi. If one further introduces an omega deformation in the TX plane, sort of localizing everything to the origin of that plane, this can be done precisely when your theory is superconformal. Then the operators I'm talking about only live in a single holomorphic plane, and now they can have singular OPEs, and that leads to the story that Beam lend was leyendo, Taylor-Zerstelli-Van Rees work out, and the VOAs that Madeleine was talking about. So this is a different way of accessing the same VOAs. I won't say much about this omega deformation. In fact, I'm going to introduce things that explicitly break this omega deformation. And I'll just be working with basically the underlying vector space of this vertex algebra. I want to know what Q-cohomology of local operators looks like. Some structural things to note. So local operators in general, but in particular the space, is graded by the Cartan of an SU2 R symmetry, under which our differential Q has degree 1. This is a cohomological grading, and there's also a spin grading that, after being adjusted a little bit or mixing with the R symmetry, can be adjusted so that the supercharge is invariant. And so this just looks like an additional grading that has nothing to do with cohomology on this space of local operators. And it's the conformal grading. So Z derivatives in particular have degree 1. The Schur index then is a generating function. It counts the graded dimensions of this cohomology V with a -1 to the R and a Q to the spin. In general, if the supersymmetric theory has extra flavor symmetries, we can throw in some extra fugacities for that. I won't actually do it today. The examples I'll talk about are in our pure gauge theory. That was the simplest thing for us to start thinking about. Though there should be interesting generalizations to other theories. I'll also point out pure gauge theory is not conformal. Nevertheless, the techniques I'll discuss work just fine. To give a flavor of what this Schur index looks like, it's in physical terms, the operators in Q-cohomology are two gauginos. So if one just does a classical analysis and asks in pure gauge theory, what's killed by Q, you get two gauginos. And so in abelian theory, these are neutral gauginos. And one gets the gauginos and all of their dz derivatives, all of their modes in the holomorphic plane. They're fermionic, and the index of, or the generating function of two sets of fermionic oscillators sort of looks like this. It's the square of this Q infinity symbol, where the different modes are sort of all put into there. And for arbitrary group G, one gets a similar sort of thing. So the modes of the two gauginos, which are now sitting in the adjoint representation of the group, give a generating function that looks sort of like this, or a character that looks like that, where I've used U to keep track of gauge charge. And then at the end of the day, physically, we should project to gauge invariant. And that's done via an integral over a Haar measure. And so all the complicated stuff up front is really just a Haar measure. So so this bit says project to G invariance. Okay, so this much is like super well understood by now. What are we doing? Part of the goal was to try to understand a different perspective on the space of local operators, and also not just give its index, but describe the actual space. And the way we're trying to do it is in terms of some sort of TQFT categorical structures that arise in the topological R2 plane. This includes looking at line operators that are supported at a point in the holomorphic plane and some line in the topological plane. These form a category, and I'll say a little bit later on what that means and why that happens. Possibly I'll say it here. Maybe first physically, the line operators that I'm talking about are ones that also preserve the supercharge Q. In physical terms, that includes half BPS and quarter BPS line operators. And the half BPS ones have been very widely studied in lots of work. Gayoto-Mornitsky in particular comes to mind in terms of algebras of these operators and cluster algebras and so on. But these are Wilson et Hooft lines. So they have some electric charge and some magnetic charge. And they're the objects of this category, and the morphism spaces in this category, there's some vector spaces. Their morphisms compute Q-cohomology of local operators at a junction of lines. And the way I eventually want to use line operators to access local operators, which may seem a little backwards in that I'm using something potentially complicated to access something simple. Well, what's going to happen is that there will be some geometric description of this category. There is an object in that category that's the trivial line, the like do nothing. It's the equivalent of the identity operator in CFT. So a junction between the trivial line and the trivial line it just contains bulk local operators. And so by computing this morphism space in this rather complicated category, one should be able to reproduce bulk local operators. So that was one of the initial goals here. And I keep forgetting to say it, but like everything's in Q-cohomology. And then I'll do an even worse thing. Because lines weren't complicated enough, I will access lines via surfaces. And I'll do the same thing. So there's a two category of surface operators. And if I look at junctions between the trivial surface and the trivial surface, I'll end up with the category of lines. And that's actually, for me, the cleanest way to identify what this category of lines actually is. So I'll talk about surface operators in a moment, but they're exactly like, they're a generalization of what Maddalena was talking about, just to supersymmetric theories. Conformal is not necessary here. And then the thing that I won't talk about is boundary conditions. So there's an analog of the Schur index that counts boundary local operators that I think I first wrote down in a paper with Gayoto and Gukov long ago, where our goal was to study something very different, having to do with the 3D correspondence, but this was convenient. Anyway, so this half index and boundary local operators also fit nicely into the whole categorical framework, and one can reproduce bulk local operators by sort of gluing two half spaces together along boundaries, which is the direction this is going in, but I don't think I'll have time to say anything about that today. So sort of like physical motivation is to like try to use some geometry to get another perspective on various operators in Q-cohomology. There's also a math goal that I'm not going to say almost anything about, but is probably the most non-trivial and newest part of the story. Like what I will say here, like, I think a lot of people could say this and make the relevant connections, but then at the end of the day, you get to a really hard mathematical computation, and we're sort of trying to find the right mathematical language to compute all these things in, which involves some version of derived algebraic geometry, and we, and in particular Wenjun, is like pinning down the precise version of the math that gives sensible physical results. Okay, so my plan for the rest of this is to go back to surfaces, and then reduce from surfaces to lines, and then from lines to local operators, and try, at least in pure gauge theory, to say what how local operators are recovered from what a priori is something very complicated. In terms of notation, I want algebraic models for everything, which involves using complex reductive groups rather than compact groups. So I'm going to do something physically horrible and call the gauge group GC. So GC is U1 or SU2 or UN or whatever, and G is going to be the algebraic group. It's complexification. So surface operators. So here we're looking at extended operators supported at along the topological plane and at the origin of the holomorphic plane. Like I said, they include, oh, sorry, I didn't actually say this. They not just include, but they are always half BPS. So if one actually wants these to be topological along the R2 plane, it's that plus the condition of preserving our single Schur supercharge Q actually means these had better preserve an entire 2D n equals 2, 2 supersymmetry algebra. And these are generalizations of Q-cohomology surface operators and have been studied in many other places. I will say that the description I give in a moment will generalize like Q-cohomology type constructions in a way analogous to what I did with Garner, Gerasi, and Hilburn, trying to describe 3D n equals 4 line operators and some algebraic constructions of Justin Hilburn and Phil-Seng Yu. So I'll explain what I mean by generalizing immediately. So how do we figure out like what sort of data describes the surface operator? One nice way to do it is to compactify space-time along a circle that links this surface operator. And so physically, one can think of taking this holomorphic plane and deforming it into a cigar where the surface operator is sitting at the tip, and then like shrinking the circle of that cigar. And I don't mean shrinking in the sense of just keeping zero modes. That's a holomorphic plane, and so the precise thing you're supposed to do here is to look at BPS equations for the supercharge you're using, but those don't fix you to those don't restrict you to constant field configurations along the circle. So at the end of the day, let me say this in steps. So geometrically, what happens if you sort of ignore this circle in the cigar, you end up with a three-dimensional theory on a half space where the original surface operator has become a boundary of the 3D theory. The gauge group, however, is no longer just the group G, but rather the loop group. And in physical terms, one ends up with a 3D n equals 4 theory whose group is the loop group of the compact thing. The keeping track of supercharges, the holomorphic topological supercharge from 4D has become a purely topological supercharge in what at least some of us call the B-twist of 3D n equals 4 theories. So their 3D n equals 4 theories have two topological twists, and this is the one that Rosansky and Witten used and Blau and Thompson first wrote down, and Kapustin, Rosansky, Salina said a lot about its categorical structure. So one ends up with boundary conditions for a 3D TQFT. This original two category of surface operators should be the same thing as the two category of boundary conditions in the 3D TQFT. And once you know that the 3D theory is like 3D n equals 4 pure gauge theory, and there's actually a beautiful geometric description of what objects in this category look like. In other words, like how do you define a boundary condition in 3D theory with gauge group G? Well, you take geometrically, take a sigma model into a space that has a G action, or even better, so I'll describe this here in terms of sigma models, but more generally, just take any two-dimensional theory with G flavor symmetry and couple it to the bulk by gauging the G flavor symmetry. That is a completely general description of defining boundary conditions here. Now you have to make sure that supersymmetry and so on is preserved, and so the spaces that we're acting on had better be Taylor manifolds, and in translating that into an algebraic context, one ends up with algebraic varieties that have an action of the algebraic version of the loop group, which is this thing I'm denoting G double round bracket Z. So by that I mean the algebraic group G defined over Laurent series. And so if our initial compact group was U1, the group is C star, and defined over Laurent series, the algebraic loop group is Laurent series that are not zero. Or for SL2, we'll get 2 by 2 matrices of Laurent series such that the determinant is 1. Okay. So that's a very abstract construction. So I ended up with this conclusion that we have this two category of surface operators. Objects in it are algebraic varieties with a loop group action. You can actually think about that physically a little bit better by in a different way, by just thinking about a neighborhood of the support of the surface operator. So if we work in the holomorphic plane and we sort of remove the surface operator itself and look at a punctured neighborhood, and note that in this particular holomorphic twist, the gauge group effectively gets complexified and gauge transformations have to be holomorphic, then there's sort of the gauge group in this punctured neighborhood of a surface is this loop group that I was talking about. It's G defined over Laurent series. It's gauge transformations on a tiny punctured disk. And so again, given any 2,2 two-dimensional theory with flavor symmetry loop group, I can couple that in by gauging its flavors.
Question.
Yeah.
Will the objects be honest algebraic varieties, or will they need to be int varieties or something? Like a natural candidate might be the affine Grassmannian.
Yeah. So right. So that's the next example. Yeah. So they will be. No, this is exactly where the math gets complicated and what I'm sweeping over in a horrendous way. So they will be in schemes, like derived in schemes.
Great. Thanks.
We need to figure out how to do any sort of computation with that.
Yeah.
Yep. Right. So the most trivial example is the trivial surface operator, where nothing is actually inserted, the trivial surface operator has a non-trivial description in this setting. What one notices physically is that, in fact, there's no puncture in this little disk. And so in some sense, like the Laurent series gauge transformations get broken to Taylor series gauge transformations if you fill in the puncture. And the way to implement that breaking via coupling to a sigma model is to couple to the coset space, where so we take G defined over Laurent series divided on one side by G defined over Taylor series, where there's still an action of Laurent series on the left. So there's an action on the other side. And this space is the thing that Matt just mentioned, the affine Grassmannian in mathematics. It's an infinite dimensional space, and it's a highly singular infinite dimensional space that needs to be defined very carefully. So just to connect with other things that have happened in physics, so like more standard sort of Gukow-Witten-ish surface operators, like in physical terms, you would say that at the surface operator, you break the gauge group G to some subgroup in finite terms, and that also has a description in this Luby language that I think I'm going to skip over. But this is sort of this is a very general way of, in fact, all surface operators that I know of in Lagrangian theories come about this way by coupling to an appropriate space. Okay. So to get from surfaces down to lines, we will consider junctions of surfaces. So in TQFT sort of terms, morphisms in this 2 category whose objects are surfaces are going to be the sets of lines at their junctions, but these sets of lines themselves form a category, and categorical level goes down. So the picture is sort of what's drawn here. So we have a junction between 2 surfaces, and there are all sorts of possible lines that could go at that junction. And everything is supported at 0 in the holomorphic plane. Right, and then there's a computation. So guided by what happens in 3D, one is led to at least naively write down that this space of junctions between 2 surfaces labeled by varieties x and y is going to be coherent sheaves on the product divided by the diagonal action of the loop group. And where, just sort of quickly, where that comes from is in this 3-dimensional setting where you think of these surface operators as boundary conditions in a 3D theory and like enfold a book closed. And reduce that 3D theory with 2 boundaries and a junction to a 2-dimensional B model. And the target of the B model is precisely the product of whatever you had on the 2 boundaries, and it has gauge group, loop group. And the category of boundary conditions in this 2D B model is what I just wrote. Okay. So then we apply this. The thing, like the most trivial thing I could be after is the category of line operators that are not sitting on surfaces, that are just line operators in the bulk. This category that has Wilson and 't Hooft lines. And we'll get it as hum between the trivial surface and itself. And then we use this, erase that. We'll use this geometric prescription. And what does that tell us? So we get two copies of this coset space, Laurent mod Taylor, and we'll divide by a diagonal copy of Laurent series. And when you do that, well, there's a loop group on the bottom and a loop group on the top that cancel. And one ends up with a single loop group on top and two sort of Taylor series acting on either side. And so at least the naive guess is that one ends up with coherent sheaves So here I've taken the action on one side and turned it into equivariance in the category. That again is part of the mathematical way of dealing with this. But one ends up with coherent sheaves on the space, and this is a familiar space in many ways, which I'll get to at some point. Okay, so that's the guess for the category of lines. When the dust settles, one gets coherent sheaves on the affine Grassmannian, which are equivariant for the left action of the group defined over Taylor series. This thing was written down by Kapustin at least a decade ago in a paper about holomorphic reductions of 4D n = 2 theories. It contains, as I said, Wilson and Hooft lines. The Wilson lines are, the way electric charge comes in is through this equivariance under a copy of G defined over Taylor series. The way magnetic charge comes in, the way its Hooft lines show up is interesting. Essentially a magnetic charge defines an element of this loop group in the middle. And then one can consider the double coset of a particular element of the loop group. And so I've given a little example here. So if our group is PSU2 and we want an Hooft line with fundamental charge, we'll take this matrix in PSU2 and take its double coset. And one would expect that there's a sheaf whose support is this double coset that is associated to this particular Hooft line. And that was made beautifully precise in a much more recent paper by Sabin Cautis and Harold-Williams. So it turns out, well, first these orbits are not compact. One can take their closure, but then the closures are very singular. And so it's not sufficient to just say, like, take the structure sheaf of an orbit closure. And there's something more complicated that one has to do, but they figured out what the right things were to correspond to what physicists would call half BPS Wilson and Hooft lines, or at least they made a guess for what they should be. And also part of the point of what Wenjun and I have been trying to do is to see whether that's sensible in various ways.
So question, these closures and dealing with that is about the problem of monopole bubbling. And
it is, yeah, physically it's monopole bubbling. And the math answer, there's an expected answer, which is related to the last thing on this slide. So like this whole story is related to the Satake category that shows up in the Langlands twist of 4D n = 4, and to descriptions of monopole operators in 3D n = 4. And in the Satake category, you're supposed to look at intersection cohomology sheaves. There's a coherent version of IC sheaves that is supposed to solve the problem.
Yeah.
So like if you ask a mathematician, there's no issue with monopole bubbling.
Yeah.
There's a canonical thing that you write down.
Yes.
Yep. Yeah, I should also say this is a monoidal category, like lines sitting on the trivial surface can be collided in the topological direction. And if you look at what that means in K-theory, you end up with like sort of a GMN, Conceived-Soibelman cluster algebra story, and difference operators. This all ties into many other things. Okay, so that's what the category of lines looks like. And now let me do the thing I said I was going to do at the beginning. So let me believe that this is the right category of lines. And also, like, I should caveat, like, I have not given you a proper definition of this category because as I didn't address the thing that Matt wanted, that the affine Grassmannian is some derived in scheme, and one actually needs to treat it that way. But surprisingly, one can, and can make sense of this. And then let's just be naive and try to figure out how to extract local operators out of this. So playing the same sort of game, we'll take hum in this category. Hum between two lines is local operators at their junction. And I say hum, and I had a little note to myself. Everything's derived. So in depending on what language you want and are familiar with, I really mean like X as a complex. In particular, if we want bulk local operators, we should take hum between the identity line and itself. And then we need to identify what the identity line is, or the trivial line. And so that's a line of magnetic charge 0. And so that should be a skyscraper. Well, so that should be something supported at the double coset of 1, of the identity element of the loop group. And that ends up not being ambiguous. There's no monopole bubbling when there are no monopoles around. And one ends up with a skyscraper sheaf supported at the, it's sort of the coset of the identity inside the affine Grassmannian, and it's invariant under the left action of Taylor series. And so I'll just denote that as O of 1, and I mean the skyscraper sheaf at 1. And then we compute. And let me just explain. I'm going to give you the very naive version of the computation without all of the interesting hard stuff. So why would you even expect this to work? So we've got a skyscraper sheaf at a point in the affine Grassmannian. It's a two-step computation to find its derived endomorphisms. First one, depending on one's background, one might know or remember that endomorphisms of a skyscraper sheaf are given by an exterior algebra in the tangent space at that point. So this is familiar physically in the B model. We're talking about in a B model is a Dirichlet boundary condition that kills bosons and has a bunch of fermions around, and these fermions are giving you sort of infinitesimal deformations of that Dirichlet boundary condition in the B model. Or you can just take this on faith since I have 3 minutes left. So one expects to get an exterior algebra in the tangent space of the identity coset in the affine Grassmannian. If you just treat this tangent space very naively as a vector space, it looks like the Lie algebra of the loop group mod the Lie algebra over Taylor series. And that is just the Lie algebra with polynomials in Z inverse. It's the part that Taylor series doesn't kill. With the constant mode removed. And so you get little GL2 example, and I'm using GL2 just so I don't have to set the determinant to 1. So we get a big matrix of series in Z inverse with no zero modes. And we're building an exterior algebra out of this thing, so all the modes are fermionic. And the way to package that all up is to just say that we have non-zero modes of a Lie algebra valued fermion. And if we remember that everything should also have the structure of a vertex algebra, it's just a very natural way to write that, which ends up being what actually happens is that we have a fermionic field and all of its non-zero modes valued in the Lie algebra. That ends up being half the story. So when I did this computation, I didn't take into account the fact that there was some extra equivariance and that there was a Taylor series action on the left. In the equivariant category, when one takes Hom in a derived way, one has to first compute the space, this big exterior algebra, and then take its invariance under the loop group action. Now, the loop group is acting trivially here, except for its constant modes. Oh, sorry, that's not. Let me finish the talk before getting caught up. So taking invariance under this group defined over Taylor series in a derived way means introduce a ghost. And the right way to do that is to introduce ghosts for the non-zero modes and take constant G invariance by hand. And that gives you another Lie algebra valued fermionic field and its all of its non-zero modes. And so the upshot of the geometry computation at the end of the day is that one ends up with what looks a lot like, and I've sort of packaged it this way, it looks a lot like the G invariant part of a commutative vertex algebra just generated by the non-zero modes of two fields, which I have very suggestively called B and C. But this is not a BC system because the OPE, again, the OPE is non-singular. It can't be made singular in this case because we're not dealing with a conformal theory. And that's the right answer. So, so first, that agrees with, for example, what Owen Yagi wrote down in their analysis of Q-cohomology in a different way. And it beautifully agrees with the Schur index. And so what we've gotten geometrically as sort of a fermionic version of the cotangent, a fermionic version of the tangent bundle at the support of the skyscraper sheaf and derived Taylor series invariance is the same thing as these two gauginos. They're the two halves of what the Schur index was computing. And so the modes of B and C are in here, and then we take G invariance by hand. And so at least that part, so like that part works out. And again, there's a lot of hardcore math behind this, and making sure that actually makes sense in some version of infinite dimensional derived geometry. And just to finish up, we can also, in fact, fairly easily compute local operators at junctions of at Hooft lines or Wilson lines or whatever. Wilson lines is easy, but at Hooft lines is quite non-trivial. So we can get the vector spaces of these operators at Hooft lines, and they have the right indices. Were written down by Cordova, Gayota, and Shao. The indices. In order to sort of prove more generally that the mathematical prescription defined properly actually agrees with physics, it seems that a useful way to go is to actually break everything up with boundary conditions and think about actions of bulk lines on boundary conditions. And that seems to be working out. Sorry, I haven't said much about it. much more interestingly, the chiral structure that like either the commutative chiral algebra or in a superconformal theory, the really interesting VOA that Madalena talked about should sort of be combined into this. And at least without omega background, when it says that the category of lines and the two category of surfaces should be chiral categories, which are a very abstract thing mathematically that I would love to understand all of the physics of. And so that takes into account moving in the holomorphic plane as well. And finally, I would hope that there are cool things to say about dualities and UVIR maps and cluster algebras and maybe even extend this sort of thing in a clever way to class S. Be fun to think about that later on. Thanks.